Okay, thanks Sylvia for the introduction. So I'm going to talk about fluid structure interaction by the PFEM particle finite element method as it's been implemented in OpenSees over the last couple of years by my PhD student, N.G. Ju. So a quick question, when you see the OpenSees logo on the webpage, does it scream earthquakes? The wave that's crashing? So it's about time somebody did something with water in OpenSees to fit the homonym. Okay, but so fluid structure interaction's been in the focus of research in the last few years, or it's been a long-standing source of research, but particularly with some of the recent natural disasters, earthquakes and tsunamis, 2004 Indian Ocean and 2011 Tohoku. There's also one in Chile. In between there they didn't list, but tsunami or fluid structure interaction is becoming a new topic of research, and with performance-based engineering and whatnot, starting to look at wave loading on structures. Okay? So anyway, documented structural failures are going to have and simulation implications on design codes, and of course designing new and strengthening existing infrastructure along the coast, like bridges and tsunami evacuation shelters, for forces that they may not have been initially designed for, drag, impact, uplift forces, serious implications, especially bridge decks that can uplift, bridge decks that aren't even tied down could uplift when waves come and lift them up. Okay? And there's various simulation approaches for FSI, finite element based, arbitrary Lagrangian or Lagrangian. Different fluid type simulation approaches have been around. And typically structures are assumed to be rigid, which could be unconservative in terms of the forces they can resist. And so starting to look at this particle finite element method, which uses a Lagrangian formulation that's comparable to what's used in structural finite elements, where the position and physical properties of the particles are described in terms of material referential coordinates. Okay, so you track nodes or particles, essentially the same thing, and then create a finite element mesh with fluid elements, track the free surface and the evolution of the or turbulence and evolution of the free surface. Okay. So this PFEM has been developed over the last 10 years or so, mostly out of Spain. We've decided this could be a practical way to do FSI with an OpenSees because it fits in with the Lagrangian formulation. Okay, so it's kind of natural for solving fluid structure interaction problems. So the basic steps of the PFEM analysis creates an initial discretization of particles, and the particles are where we track velocity and pressure. So that's kind of the state of each part. Okay, and we kind of assign different particles for being in the fluid domain, and particles are nodes within the structural domain. Okay. And then we create or triangulate the fluid domain, create fluid elements for incompressible or compressible fluids, and then create structural elements from triangulation. We do solid elements or frame elements, as I'll show an example. So we can kind of mix frame elements with fluid loading fairly easily with this PFEM approach. And then the analysis loop is whatever particle positions we have, we do an analysis and then remove the fluid elements, and then particles move to new positions, we retriangulate the fluid domain, go to the next time step, and repeat. So we need a really good mesher to pull this off efficiently, because we're remeshing at every time step, just the fluid domain, not the structure domain. Okay, so there's some commands that have recently been added into OpenSees that allow us to discretize domains into particles and then triangulate to create elements. Okay? So for example, this is the command to create a rectangular grid of particles or nodes. You can use it to create nodes for a structural model if you wanted. There's nothing special here, but say we want a rectangle. We supply a starting node, an x and y coordinate for the lower left or the origin of the rectangle, kind of an angle of rotation. Theta, the number of grid spacings along the x direction, grid spacing along the y direction. And then there's some optional arguments for fixity, mass, initial velocity, and boundary codes that I'll talk about next. So this is all in OpenSees, and if you want to run a simple FSI type of example, we'll first create particles. Okay. And there's some description of the optional commands. The fix, which is the boundary condition applied to each particle, akin to the fix command that you've seen for the structural models. Okay, so we'll create a bunch of particles that can all be pinned or rollered, if you will. Structural engineering speak here. But default, all the particles are free, so 0, 0 is the default. But we can completely fix them, like for a wall or a bottom surface that contains a fluid. Then mass is assigned to each particle. By default, there's no mass. Initial velocity, if you want to have like a tsunami bore of some initial velocity, prescribe it for those particles within that domain. Okay, and then the boundary list kind of indicates whether or not to include particles on the sides of the rectangle. Because for triangulation reasons, we can't have particles overlapping each other, so we have to kind of jitter or offset the particles manually, or just tell the discretize command not to discretize along an edge. So one is include, 0 omit. By default, we discretize on all boundaries, but if we give a boundary code of 1100, then we would only discretize on sides 1 and 2, but not 3 and 4. So these particles would go away, and these particles would go away. So this is, try Andreas's trick from yesterday. I think he was able to get the pointer here with the shadow, but so this is side 1, side 2, side 3, side 4, right, as numbered here. Okay. So when you put one rectangle up to another rectangle of points, you don't want them necessarily overlapping because the triangulation will take a poop on them. Okay, but anyway, that's the command. But kind of an example here is shown with the display command from OpenSees, which just creates a little window that we can show the points that are created from the discretize command. So discretize rectangle. We supply a starting node, which is the tag of the first node that's created, right? And then the x and y location is 5, 3. And then the grid spacing in the x direction is 2 units and 1.5 units, 30-degree angle of rotation, and then 4 spacings along the x direction, 3 along the y direction, and then there's 2 degrees of freedom for each node. And this command will return the tag of the last node that's created. Right? So it numbers sequentially from starting node, which you supply to the command. So this is 1, 2, 3, 4, 5, and it goes up to 19 or 20. Yeah, 20. So 1 through 20. So end node will be set to 20. Okay? And we'll see why that's useful later. So this is just the particle or node positions that are created by that command. Okay. So if you do perhaps should have mentioned this first, but doing the PFEM analysis, it's only in 2D at the moment, and you need to use only 2 degrees of freedom per node or per particle. Right? And then the pressure degrees of freedom, kind of the third degree of freedom, are created internally, but explicitly say there's 2 degrees of freedom. The pressure being left, kind of hidden from view, if you will. Okay. We can also discretize other areas or regions, such as lines, triangles, circles, and planar straight line graphs, which is just a bunch of points that are allow you to do kind of arbitrary discretization into a group of points. Okay, then after we have a set of particles, right, we can go in and do the triangulation with a command called do triangulation. Right? And this is the basic syntax of it. Right? So to create fluid elements, or to create, we can do fluid or solid elements, but for fluid elements, we have a PFEM element, 2D, right, which is what this last switch is, and then element properties of density, viscosity, body forces, and out-of-plane thickness. Right? And then we tell which nodes we want to, which range of nodes we want to triangulate over, right? And then pass in the starting node tag and then the end node tag for that. We also pass in the starting element tag, and then the command will return the tag of the last element that's created by this command. Okay. So just doing basic triangulation that you have seen probably earlier today or yesterday. So for example, if we triangulated that region of particles that we just looked at, we could say PFEM2D, do triangulation. That 1.4 is the alpha shape parameter, which kind of clips off particles that are too far from other particles, such that you don't have a particle here and a particle there that really shouldn't be connected, so it'll clip those out. Usually 1.4 is good enough to take that as is. Okay. But the command is shown here, where we have the starting element tag. You set the 1, it returns the ending element tag, which is, I think it looks like it creates 24 elements. Okay. Numbers sequentially from what you supply to what the last element is. And then the thickness, body forces, viscosity, and the other element arguments. So we end up with something like this. And then we can also triangulate solid elements. If we had another group of particles or nodes that were meant to be in the structural domain, we can use the tri-3-1 or triangle 3-1 elements. Right. Again, with starting element tag, thickness, type, plane stress, plane strain. And in the material tag, elastic, isotropic, or whatever. And then optional arguments for the density, body forces, and pressure. But it's surface pressure, not traction load. Okay. And we can also do line element discretization to get solid elements, or structural elements, I should say, that are truss or frame. Okay, so all the elements we know and love from earthquake engineering applications, like with fiber sections and co-rotational transformations to get material and geometric nonlinearity, they can be used with this PFEM analysis. So you can take your building model of a reinforced concrete frame, fiber sections, and throw some fluid at it and see how the structure responds. But in order to develop an interface between the fluid and the structure, you typically have to use very short element lengths, such that there's nodes there that can connect to particles and form interface elements during the analysis. Okay, and then we've seen analysis static, analysis transient, right, which form external forces equals internal forces for static, or for transient, external forces equal static resisting forces plus damping forces plus mass, or inertial forces. Okay, but in PFEM we form, there's also momentum, or conservation momentum equations and conservation of mass, which are the governing equations. So it's a different type of analysis, different types of classes and objects have to be created. But to tell OpenSees that we're going to do a PFEM analysis, so analysis PFEM, and then we supply it with the min and max time steps used in the simulation. And then we have a convergence test, which looks at the incremental velocities and pressures, as well as the residual or right-hand side values associated with velocity and pressure, and then also relative values, or values relative to the first iteration. So analysis, convergence test, same kind of setup as solving the wave equation. then kind of you have to write a loop to do the analysis. There's no nice analyze 100 steps, at least not yet. But we just loop through time, do an analysis with the analyze command. And if everything goes okay, we go in and remove the fluid elements using the remove element command, which is available in OpenSees. So here we're looping through the tags that the triangulation command is returning to. So we know where we started, but we don't necessarily know how many elements are created at every time step. We can store it in variables. And after we remove the elements, we then reset the influid tag by doing another triangulation. Okay, because the number of elements could change from time step to time step. But then when we come back through, we're just looping from start, which is fixed, into the end tag, and remeshing, and redoing the analysis. Okay, so an example kind of made up the other day, but it kind of demonstrates what can happen. So we have a fixed boundary on the left and a fixed boundary on the bottom, okay? And kind of a column of water, a column of fluid here, right, which is in a nice rectangle here. Assume there's like a super piece of plywood here that's holding this water back, all right? And we're just going to lift it up instantaneously and then let it swoosh down and hit this structural or elastic column. So there's a little bit of separation here to let the water flow. The column is elastic and it's basically going to act like a rubber band and hold the water back. Okay, so first we just go through and we can use the discretize rectangle command to create this rectangle, this rectangle, this rectangle, right, and then create a bunch of beam elements along the height of that structural column to do our analysis. Okay. So the discretized rectangle for the left wall, okay, we create a grid of 48 points, which is at -4. And so the origin is here at the lower left corner of the water column. So I'm just going over here, -4, -4, and then grid spacing is 2 units. The number of X divisions is 2, or and 15 in the vertical direction. So that's what the 2 and the 15 mean over here. And then we're fixing all these particles against translation. Okay, so the fix 1, 1 is there. So it's like we're pinning each one of these nodes from moving. But they can still develop pressure, which is what's required to keep the water from leaking through the wall. Okay. Then we can issue the discretized rectangle command again to create the bottom surface or bottom floor here, which is also fixed. And it has the same grid spacing of 2 units. There's 20 intervals in the X direction, 2 in the vertical direction, and then fix 1, 1. And then the boundary codes, we don't want to create more particles or duplicate these particles here, so we do the 1, 1, 0, 1 on the boundary discretization. Which this is better than trying to offset it manually, move the coordinates around. Okay. And then the fluid domain is centered at 0, or lower left corner at 0, 0. Use a finite grid spacing of 1 unit in each direction, and it's a 20 by 20 grid of points. And then the boundary, again, we don't want to create more particles down here or over here, so our boundary code is 0, 1, 0, 1. Okay, so no extra particles down here or over here. This is side 1, 2, 3, 4, 0, 1, 0. All right. Then we can, once we have all those particles, we can triangulate with, starting from the nodes. And we set W0 initially to be 1, and then we did the first discretize and got W1 number of nodes, and then pass W1 plus 1 to the starting node number. Here we got W2, and then W2 plus 1 to W3, so we want to go from W0 to W. I don't know why I called him W. Call it anything we want. So. Peanut butter, jelly.
Water?
Probably water, yeah. And then create the fluid elements dash PFEM element 2D, the starting element tag of E0, which is 1, which is E is element. A density of 7,800 kilograms per meter cubed is probably where I got that from the water. And then the body force of negative G, and how the plane thickness. So the numbers are kind of made up. Some of them are real, some are physically used. Okay, and know this constant. Okay, so that gives us, or gave us, all these fluid elements, which these particles are not restrained from motion. But we also have to develop fluid elements along the boundaries such that we can develop pressure that resists the water from leaking through the walls. So we do need the elements on in the fixed regions to these little triangles. Okay. And then using the commands that we've looked at before for beam column elements, we can discretize a line from here to here to give us a bunch of nodes, and then write a simple loop that creates a bunch of displacement-based beam column elements with elastic sections and the co-rotational transformation. So the co-rotational transformation lets us get away with not having to remesh the solid elements or the beam elements like we do with the fluid. We can track the large displacements pretty easily for the structure. So that's what we did here. Just discretize this line, okay, and then write a little loop, create short elements. And if you're going to use really short elements, don't bother with B1As or that garbage. Just use the displacement-based elements. Okay. So we remove the plywood, release the water column using a time step of 0.01 seconds. We can kind of see at about 0.5 or at half a second, the water is starting to impact the column here. And I don't think I mentioned it's fixed down here, and then vertical roller up here. So it's like a column that's fixed and pinned. And at 1 second, the water is starting to really impact the beam or the column there. You can see some very large displacement. This is not amplified. Scale factor is 1 on the display sheet. Then at 1.5 seconds, it's ridiculous. Academic sort of example here. But this point is moving down. It's getting some large displacements there. But with very short elements with the co-rotational transformation, you can track that kind of behavior. But the structure is holding the water back, right? So it's doing what it's supposed to do. Okay. If we have another example I can show after. So, of course, current and future work extend this to 3D high-performance computing, which we've talked about already. We're also looking at compressible fluids, which are numerically a lot easier to do than incompressible fluids. Kind of like structural dynamics is easier than rigid body dynamics. Same kind of goes for fluids. And then further stabilization for numerical purposes, reliability analysis of the structural response, and then debris and impact modeling coming down the pipe. So I started creating a wiki page on the OpenSees site for the PFEM analysis. There's a paper under review submitted last month, kind of detailing the implementation within OpenSees. Knock on wood, I hope soon it'll say accepted for publication, or you'll see it under review in a different journal the next time I give this presentation. And just acknowledge the sponsor there. Let's have a few more minutes. Sylvia. Yeah. Okay. All right. So, let's see. Yeah, so here's a reinforced concrete frame. These are the beam cross sections. Here's the column cross section. Now I realize I did this all backwards. So to the U.S. National Conference on Computational Mechanics, I showed them the fiber model building, and they're all like, yeah, whatever. I should have shown them the elastic thing. Looked like a rubber band. Computational mechanics, yeah. But and I should have shown you guys the reinforced concrete frame, but since we have a little time. But anyway, I'll stop trying to be funny. And we have the girders, the column cross sections, and the stress strain behaviors for the confined and unconfined concrete. So using the same models that you've seen, today and yesterday for the member response. If we look at this building being impacted by a tsunami bore, initial height 4 meters, which is about the height of the first story, velocity of 2 meters per second. And this is kind of the initial configuration, and then 1 second, 2, 3, 4, 5, 9, 12. We see it about between 3 and 5 seconds, or 2 and 5 seconds is when the water impacts the building. We would expect the largest displacements and forces in the building. And then we can plot time histories of the roof displacement, or the floor displacement. So up here is the second, third, and roof floors, all the time histories. And then comparing a linear elastic material behavior with nonlinear concrete 01, steel 01 type model. See, for the nonlinear materials, we get displacements about 3 times higher, which you would expect. But really what we care about is the forces, which aren't currently coming out properly, so all I showed is the displacement from history. Presumably, if you can get the displacements right, the forces should ensue. That's not always so easy when we're dealing with pressures and things like that. We'll get into eventually. Okay? So, I think that's it. But again, the point is, we can use our earthquake engineering models, fiber models, and do wave loading on those, and this could be the simulation framework for performance-based tsunami engineering, if you will. We could demand parameters based on different loading conditions. Typically, you do these tsunami bores where it's some height of water with some initial velocity, and then you throw it at it, or let it release. Forms a little wave here, crests and breaks, and then turbulent flow around this area. It's the structure. You get some kind of a. It's very much under development, but I think we're getting to a good point where we can get some results. Hopefully soon we'll be able to get some forces, reliable calculation of forces induced in the structure. So, any questions? Sylvia?
For the 3D implementation, do you envision being able to just really capture the waves going through the building and then coming back and being able to go around?
Yeah, so we could Yeah, and the waves, they have to go around the building or through openings, and so you can't do that in 2D at all. We can make it go kind of through the building in 2D by using a coarse mesh for the columns on the first floor. Use one element for that member. And there would be no particles along the length that would then join up with the fluid particles. So essentially the fluid would just kind of flow through the building. Like a tsunami shelter on stilts, where there's no masonry walls or walls to kind of stop the water or resist the water. But around and through, openings, you have to do 3D.
And you see that being able to go that way?
Yeah. It's just a matter of computational effort. Yeah.
I'm sorry. Follow-up question where you just said the fluid can flow through. I don't quite see how it works. That you had that one example where you had the wall on the left and the beam or the column on the right. You said on the wall on the left you had to basically use your elements because so the fluid doesn't leak through.
Right.
So how does it work on the structural element on the other side?
For it to go through, or
Not to go through? How
well, we
is that
still have a.
interaction, like, you don't have pressure there, right? Like, as the
No, there's pressure degrees of freedom created internally for the structural nodes too.
Oh.
So I didn't mention that, but yeah, they get created in this analysis too. So when you say analysis PFEM, it'll go in and create pressure at every node that's been created. Yep.
Like the fluid domain, does it give rise to non-linearity in the equation due mainly to the change of geometry? Or
Yes.
the material is implicitly linear elastic, or
Yeah, so it's a linear fluid, but it's a non-linear solution that goes through because of the mesh is changing, and there's a turbulence, and the solution strategy requires that you iterate to solve first for the velocities and then go back and do the pressures. So there's kind of some iteration there that's required.
And when you iterate, you iterate with a coupled system continuously, you don't go from one to the other.
Right.
The system can-
Yeah. So it's a coupled system, but it's doing like a predictor-corrector thing, not a staggered scheme, but it's monolithic equations where you partition off velocity equations from the pressure, assume pressure is 0, solve for velocity, then go back and correct pressure.
And the non-linearity coming from the fluid, in your experience, is it more difficult to deal with than the one coming from the structure? Or it's harder?
Yeah, it's taken, if you look at the norms that are coming out, the pressure is like the last thing to converge. So the velocity converges pretty fast, but the pressure takes a long time. And my students working on some other strategies, like with compressible fluids, where you just kind of don't even deal with you don't impose that constraint on the pressure, and it actually converges a lot faster, and you get essentially the same result, at least out of the structural response.
And in this problem, how many particles do you remember how many particles?
No, I mean probably on the order of thousands in here. And this 12 seconds of ball time or simulation time, it took like 3 or 4 hours on a single computer to run it. So not a terribly large amount of equations, but for particles, maybe like 10,000 equations total between the structure and the fluid and the boundaries. Yep.
When the structure is underwater, I think water has kind of damping effect to reduce the vibration.
Right.
Like typically in the breed period, when you include in the water pressure around, I think it is damp out the vibration.
Right. So really, I guess, depending on what you're doing, like, whether or not it vibrates is kind of moot. I mean, if you're looking at a bridge deck, that's, say, this way, and the tsunami comes here, you're just looking at whether or not it's gonna, the buoyancy and uplift forces are enough to unseat the bridge deck, in which case, you're not really concerned how it vibrates. But I mean, it would, I mean, you're right, it would damp out the vibration. You can kind of see it here. After about 4 seconds, the water recedes, and then you kind of see the damped the damped response out of the structure. Comes down. I mean, there's still some water in contact after 4 or 5 seconds. So it's trying to vibrate, but it's getting the water there. Provides the damping, brings it down. So is that what you're?
I'm thinking your math drawing may be useful for blast analysis.
Mm-hmm.
Simulate with some blast rate calculation.
Yeah, I mean,
So the particle may be.
yeah, that's something that I haven't tried, but I mean, if we're keeping track of, if you have a pressure history or something, you can
Yeah, so you
put that onto the.
source and you have a mesh with the structure.
Yeah, or you could have some particles kind of emanating from a source and then blasting out at some velocity, impacting the structure. Yes.
Can you give an initial velocity to your particles?
Yeah. Yeah, so like this, it's 2 meters per second for this example. So all the particles above the standing water, and then above this point,